Welcome to the first video for Math 103. Lecture 1, we're looking at Review 1, Sets in the Real Number Line. And the first objective that we're taking a look at is subsets of the real numbers. So subsets of the set of real numbers. And each of these sets has a different sort of symbol that we use to indicate what it is. So the first set we have are the natural numbers. And the symbol for that is just sort of a bolded N. Alright, and the definition for natural numbers. Well, just think about when a child starts counting, what number do you start counting at as a child? You start at 1, right? Okay, so you use this little brace here to indicate the set. So we start at 1, and then what does a child do? Do they say 1.5? No, the child will go on from 1 to 2 to 3 to 4 to 5. The natural numbers that a child would sort of start to count with. And on. Okay, so those are the natural numbers. Next we have the whole numbers, which we use a bolded W to indicate. Alright, whole numbers. Well, all this is the natural numbers with a 0 tacked into it. A way I remember it is 0 looks like a whole, so whole numbers include the whole. Alright. 1, 2, 3, and so on. So no fractions in this, no decimals. It's just solidly the whole numbers. 1, 2, 3, 0, 1, 2, 3, 4, 5. Next we get to integers. Alright, so the integers we use a z. And I wasn't certain why it was a z. So I looked it up on Google, and it comes from the German word for numbers. And in German, the word for numbers is Zahlen. Okay, because a lot of the mathematicians in the early days were German. So for the word for numbers, starting with z, which is why I would use z for numbers. So z for Zahlen. Alright. So integers. Well, the integers are when we now start throwing in negative numbers. Okay? So we're just building off on the rest of them. So let's see. -3, -2, -1, 0. Then we continue on with the whole numbers and the natural numbers. Once again, though, we still do not have any decimals included or any fractions. Now, let's get on to the rational numbers, which are Q. A nice bolded Q. So apparently, rational numbers are actually fractions. And another word for fractions in math is a quotient, which is, I guess, where Q would come from. So, a way we're going to write this looks a little fancy, but bear with me. It is P over Q. So a fraction, think of it like 1 over 2, right? P over Q, such that, this is what the symbol means right here, such that P and Q, alright, so a new symbol is coming in, are an element of, this looks like a weird E. Okay, so think of E for element. So such that the numbers P and Q, the top and bottom numbers, are an element of Z. Okay? So they gotta come from these numbers. P and Q should be either positive or negative from the integers. And one last thing. And Q, the bottom number, cannot be 0. Because remember, we're not allowed to divide by 0 when working with fractions. Okay. So, really fancy notation here. But it can be broken down into things that are readable. So, there is really no good way to write these out. I'll just give an example. Let's say a half. There are just so many, it's just almost impossible. It's impossible to actually write down all the rational numbers, just so you know. You could do 2/3, -4/5, and so on. Okay, so those are all the fractions. And then one other thing to note. All terminating and repeating decimals are an element of the rational numbers. Okay? What do I mean by terminating or repeating? Well, terminating, let's say you might end up with the decimal 0.71. Sorry, I'm going to bring it down in here. It's not actually part of irrational. That terminates. Okay? Even 0.712 terminates. Let's think of another one that doesn't terminate. How about 0.33 repeating? This bar up here means repeating. What does that mean? Well, it means you just continue to write 3 for eternity. It never stops. But the thing is it repeats. There's a pattern that repeats. So because it repeats, it's considered rational. Or if it terminates or stops, it's considered rational. So you might be like, well, what number doesn't repeat and just keeps going on forever? What number is that? Does it exist? Well, yeah, there is a number, and I think most people are pretty familiar with it now. It's pi. Most of us think of it as 3.14, but in reality, it keeps going on forever, and there is never a repeating pattern of numbers. The numbers just keep coming on, and none of them ever end up repeating. So, pi, 3.14, that's just the shortened version of pi. 3.14 is non-terminating, never ends, and it never repeats. So that is actually an irrational number. Okay, so irrational numbers definitions. They cannot be expressed as a ratio. Another word for fraction. Ratio is another word for fraction. And the decimal form is non-terminating, terminating, and non-repeating, which basically means it never repeats and it never ends. Okay, so that's irrational numbers. So an example of an irrational number. One is pi. Another one would be the square root of 2. And one of the other ones, not quite as well known, would be e. Okay? Now you might wonder, why are we using pi and e? Those aren't actually numbers. Well, these two were just so well known. They appeared in math so much that mathematicians were like, you know what, let's give these guys a nickname. So they called one pi and they called the other one e. And I believe this one is called e. I think it's 2.17 is e. That's the rough estimate of it. That's named e after the mathematician, I think, Euler, who found it. I'd have to check that. Alright, so let's take a look at example 1. We're going to draw the diagram of the subsets within the set of real numbers. Be sure to include examples. Alright, so all of the numbers we just did above are all in the same basket of real numbers. And the symbol for real numbers is a nice bolded R. Okay, so who's inside the real numbers? Well, all the ones we just did up here. Okay, so let's see. Inside of the real numbers, we have the main split is between rational and irrational numbers. Go ahead and do a nice split down the middle. Irrational numbers. Hanging out by themselves, they're irrational. Nobody wants to be around an irrational person, right? Okay, and then we have rational numbers. Okay. Oh, and sorry, the symbol for irrational numbers is H. I really do not see this symbol that often. Sometimes some textbooks use slightly different symbols. So this is actually a new one for me, seeing H used for irrational numbers. But okay. And then the symbol for rational numbers is Q. Okay, so then inside rational numbers, we have the integers. Which are z. And then inside of the integers, we have, let me go ahead and erase a teeny weeny bit. Okay. Inside of those, we have the whole numbers. I'm just going to abbreviate because I'm getting small here. Whole numbers, W, bolded W, And then finally, lastly, the smallest group we have the natural numbers. I'm just going to abbreviate that one and call it n. All right, I'm going to go ahead and do our examples. So let's see, an example of a natural number, 100. That works. Example of a whole number? Well, let's do one different than 100. Let's do 5. Example of an integer. Well, we can include negatives now, so let's go ahead and add a negative in. Let's do -3 for integers. Now, for rational numbers, I can use a fraction, or a terminating or repeating decimal. I'll go ahead and use a repeating decimal, 0.35. Why not? Let's be fancy. And then for rational numbers, think of an example. And your examples don't have to be the same as mine, by the way. Let's see, a rational number. I'm just going to go ahead with pi. Why not? We all love pi. Okay. So that's right there, the family of numbers that we work with a lot of the time. So let's look at example 2. Given our set A, okay, so this is sort of like a set notation here. We've named it A. Given A equal to 0, 1, square root of 3, 0.83 repeating, -15, 0.202000200002, and 0.44444, and 3/4, identify which element belongs to which of the 6 given number sets. So let me go ahead and write out the number sets first. We have our natural numbers, our whole numbers, our integers, our rational numbers, and our irrational numbers. What belongs in each set? Let's just go ahead and look at 0, the first number. That does not belong in the whole numbers, but it does belong in the... Sorry, that does not belong in the natural, but it belongs in the whole number set. 0. And it'll also end up being, remember with this group here, it'll also end up being in integers and rational numbers, but not irrational numbers. Next, let's look at 1. Aha! 1 will be part of our natural numbers, also the whole numbers, and also the integers, as well as the rational numbers. You might say, wait, 1 is not a decimal and 1 is not a fraction. But remember, any whole number can be written as a fraction. You just put it over 1. This is a very helpful trick to remember whenever you're working with fractions. Always you can put anything over 1. Okay, so... but it's not a part of the irrational numbers. Now let's see, square root of 3. Well, the square root of 3... I just forgot. I forgot to include r, our real numbers. This is going to include every number we come across. Okay, so let's see, 3. Square root of 3, that... Actually, if you plug that into your calculator, that is going to end up being a non-repeating, non-terminating value, which means it's going to be in the irrationals, but none of the top ones. But it will be included in the real numbers, because once again, real numbers is the overriding, I guess you could say, cloak of all the groups. All right, 0.83 repeating. Well, it's not going to be in this one, not this one, and not this one. It is repeating, so it's not going to be in the irrationals, but it will be in the rational numbers. Oops. Okay, so go ahead, pause the video, try fill these out yourself, figure out which numbers go in which groups, and then I'll fill them in. Okay, so hopefully you pause the video and try this by yourself. So let's take a look. The next one is -15. Well, it's not going to be in any of the top 2, but it will be in the integers. It'll also be in the rational numbers, as well as the real numbers. Next, we've got this long grouping of decimals. And looking at it, it's not ever repeating. So actually, sorry, there should be, right here next to it, there should be a ... So if you went ahead and put that in the rational numbers, you would have been correct because the ... wasn't there. But it was intended to have a dot dot dot. So because with the dot dot dot, it would be in this group. And I'd go ahead and write that down here. I don't know where that little comma came from. I just sort of carried that in. You're not supposed to be there. Okay. And then I need the dot dot dot. Okay. 2 more numbers. 0.444. So it's repeating and it's terminating. That's going to go ahead and go in here with my rational numbers. It's not irrational. So it'll go with my real numbers and nowhere else. And then lastly, we have 3/4. That's a fraction. So that is immediately going to go in here with the rational numbers. It will not go in any of these three. And it will not be part of the irrational because remember, irrationals does not take anything that is a fraction, but it will go in my real number. And there we go. All the groups are complete. Okay. So moving on. The next objective is using inequality symbols in interval notation. So, all real numbers can be found on a number line, all right? So any of those numbers we can go ahead and find in a number line. And we can relate two numbers to each other with the following symbols. So here we have a bunch of different symbols. Hopefully you've seen some of these, but we're also going to go over them, so don't worry if you haven't. All right, so what do these mean? So the first one is A is less than B. So if you're thinking of a mouth, for example, like on a Pac-Man, Pac-Man's going to go for the bigger quantity. So he's turned away from A because A is too small, and he's going to go for the big quantity, B. So it means B is bigger than A. For the next one, we have, actually let me pause and go ahead and do a numerical example. 2 is less than 6. There's an example. 2 is a smaller number than 6. So the next one is A is actually, this time, the mouth is facing A. So A is greater than B. Numerical example. Let's see. 10 is greater than 1. Next one, we have, so the main difference between this one and the one on top is that little line in the bottom, okay? So focus in on that. This little line here, that's the main difference. That's when we bring in the equal to possibility. So A is less than or equal to B. Okay, so a way to write that would be, what's a good example? I'll go ahead and do a sneaky one. 10 is less than or equal to 10. Is that true? Yeah, 10 is either less than 10 or it's possibly equal to 10. It actually is equal to 10. So the next one, we have A is greater than or equal to B. Once again, A and B are just placeholders. They're just variables. They can mean any random number. So what's a good example here? 25 is greater than or equal to 6. How about -6? That sounds fun. Yeah, throw in a negative, why not? All right, next we have A. Oh, I certainly hope this one, a symbol is recognizable. If not, you've come to the right place. A is equal to B. For example, what would be equal to each other? 3/4 is equal to 3/4. Just an example. So the next one, the main difference between this and the top is we have that little slash through symbol. So this is saying A is not equal to B. So let's see. 5 is not equal to 0.37. And last we have this weird little squiggle line. It's like the equation, a little off kilter there. So what that means is just sort of how it looks. It looks like it's kind of an equal sign, but it's not really the equal sign. So that's just saying A is approximately equal to B. It's not really. So let's see. So A is approximately equal to B. So what would be a good example? Well, just think of anything you round up with in life. Like, if you had something, like let's say you're at Ross, right? And your mom says, go find something under $15. And you bring up an item that's $12.99. Well, that's about $13, right? Okay, so those two are approximately the same. 12.999 is about 13. Okay, we wouldn't use an actual equal sign because they're not actually the same number. All right. So moving on. So we can also represent intervals in something called set builder notation and something else called interval notation. All right, so interval notation and set builder notation. And then as usual, we have graph options. So we have these weird symbols on the side, which we already kind of went over before. We have the set symbol right here. Those two things are the set. Then we have this one symbol here, which is talking about our main variable. And then the directions follow after that slash through line. All right? The slash through line, the word for this is such that. Okay. All right. So what do we have here? This is saying the set of x such that x is greater than a. So the set of numbers, or the set of real numbers, such that x is greater than a, or another way of saying it is the set of numbers greater than a. Okay, so a graph example of this would be, let's say this is a, and we're talking about all the numbers bigger than a. Okay, so there are two different ways to do graphing. Some people will use the open symbol to indicate not equal to, and then indicate with an arrow. I normally don't do that. I like to use the open circle and indicate onwards. But if you use the open circle or the parentheses, both are acceptable versions of graphing. And then interval notation would be you start at A, but you don't include it, so you use that open interval, and then you go on to infinity and beyond. And with infinity, you always use the open. Okay? The other option would be a bracket, but you never use a bracket with infinity, because you never actually touch infinity. It's not a number. Okay, so let's go ahead and work on the next ones. So the set of numbers, I'm going to go ahead and shorthand this, but numbers greater than or equal to a. The next one is, I'm just going to go ahead and fill this out first. Numbers less than a. Numbers less than or equal to a. How do we know that? Once again, we have that little equal symbol down there. Now this one's weird. This time our x value is in between two numbers a and b. So this one is actually numbers between a and b. So the next one, this is changing up because we have that little equal sign there. So for the next one, this is saying numbers greater than or equal to a and less than b. I'm running out of some room here. And the next one. Oh, there's a typo here on this one. This should look like a less than x less than or equal to b. Please go ahead and fix that in your notes. So this one very similar, but this time the equal sign is with the b. So this is going to be numbers greater than a or less than or equal to b. And then the last one is, not the last one, second to last one, numbers between a and b inclusive. What does inclusive mean? It just means we're going to include the numbers a and b in our answer. And lastly, the set of all real numbers. This is any number. All real numbers. Another way of writing that is that bolded R. So let's go ahead and plop in the examples. So for numbers greater than or equal to a, we'll go ahead and draw a little number line, plop in the a. So instead of using the open circle, this time we're allowed to include a. So I'm going to go ahead and fill in that bubble. If you don't use the bubble method, you would go ahead and use the bracket instead of this filled in circle. But as usual, I like the bubble method, so I'm going to use the bubble method. So let's go ahead and continue down with this, and then we'll get to the interval notation. So numbers less than a, well, numbers less than a, that's going to be on this side of my graph. But we're not including a, so it's going to be an open bubble again. But it's the numbers that are less than a on the left side. Our next graph. Numbers less than, or equal to a. So this time I can use that nice filled in bubble because we're allowed to let our answer be equal to a. So fill it in. Or once again, you could use the bracket. And notice I also lift my line above. Some professors do not like it if you float your graph higher. I like the floating graph above because sometimes your pen gets lost on the graph line. You can't tell the difference between where you're graphing or not. So I like to float it up. Always check with your professor though, because sometimes they prefer it one way or the other. Alright, let's see. Numbers between a and b. Well, we have two options. We have a and b. And we're talking about the numbers inside of it. All these guys hanging out inside. But we're not including a and b, so we're using those open circles. The next one we have is numbers greater than or equal to a and less than b. So the difference here is that we're allowed to let our values equal to a. Ew, I don't know what that was. Okay, that was a highlighter. So we're allowed to fill it in. They can be equal to a, but they're not going to be equal to b. So notice over here it can be equal to a but not equal to b. So we can fill in the a bubble but not the b. Next one. This time it's the reverse. It can be equal to b but not equal to a. So we'll bubble in the b this time. And remember, a and b would just be any random number that you might choose. So the next to last one, we have a and b, and this time we're allowed to include both a and b because it says inclusive. So let's go ahead and include both a and b so we can bubble them in. And there we go. And last but not least, we have our graph. But then we can have any number on the graph. I'm going to go ahead and pull out my fancy pink. Here we go. Any number. It extends onward to infinity in that direction. Ew, that looked bad. Onward to infinity in that direction and onward to infinity in that direction. Please note, arrowheads are important to show so-called infinity. Now let's go ahead and fill out the last column with interval notation. So one thing to note, in this class, I'll focus more on interval notation than I will on set builder notation. I find this notation a little confusing, and I prefer interval notation. It's a little more intuitive to me. Okay, so let's go ahead and let's see. So, when you do interval notation, you read it as you would a book. When you pick up a book, you start from the leftmost number and you read to the right, right? I would start here and read to the right. Start with the I, read to the right. Same thing happens with your graph. You're going to start with the first thing you see and read to the right. So the first thing I see is A, and it's included. So we're going to include the A, use that bracket. Think of a staple, right? You go, you staple papers together, it's included. So A, and then it goes on till, well, it doesn't stop. It goes to infinity. So we use infinity, and once again, infinity never has a bracket. Okay, so this next one, we're going to start, as usual, from the left. But gosh, there is no leftmost number. We're looking at infinity. How do I represent that? Well, negative infinity. So you start at negative infinity, and then you go, whoop, till you stop at A. But do we include A? No, because it's an open bubble. So this time we're going to use that parentheses, the not including. Okay, so once again, notice this means inclusive, this means not including. Okay, go ahead, pause the video, try to work out the other ones by yourself. Check back in with me in a sec. Okay, so for the next one, start at negative infinity, and go on till A, but this time we include A. And then for this one, left to right. We start at the left at A, we don't include it. And then we go on till we stop on the right at B, and not including. For the next one, the only difference is we start at A, but this time we include A. So we have the bracket, and then B, but we don't include B, so the open. The bottom, it's just the reverse. A is not included, but B is. And the next one, A and B are both included, so we get to use the brackets. And lastly, well, goodness, we have all the way into negative infinity there, and all the way to positive infinity there. So we'll just represent it, negative infinity to positive infinity. Okay, so let's take a look at example 3. Graph and write the following in interval notation. So for the first one, it says all x such that the numbers are greater than negative 2. Okay, so I'm going to go ahead and graph this. So my number line, I don't draw out a bunch of tick marks for all the numbers, I just indicate the most important one, which we're looking at is negative 2. Once again, this is something that depends on your professors. Some professors will want you to indicate where 0 is, others will want you to tick mark everything out. For me, I just like it if you indicate where the number is. If you want to indicate where 0 is, that's actually a good idea as well. Okay. And then we're saying we want everything that is greater than negative 2, but we're not including it. So there we go. Greater than negative 2. My interval notation for this will be, let's see, we start at negative 2, but we don't include it, and then we go on till infinity. And there we go, my answer. Go ahead and pause the video and try the other two by yourself and check back in with me in a sec. Okay, so hopefully you paused it and tried it out by yourself. Here's my graph. Here's 7, where that's 0 and 7. Was a 7. Now it's a 7. I'm looking at numbers that should be less than or equal to 7. So smaller numbers than 7, and it can be equal to 7. So I'll go ahead and fill in the bubble. Once again, please notice, I will be looking for the arrowheads as well as a nice filled in bubble. Interval notation for this will be negative infinity to 7, and we're including 7. So we use that little bracket for including. And the last one, ooh, getting sneaky. So the last one, we're looking at numbers where we have our values are in between two other numbers. So let me go ahead and plot those two numbers that my graph is in between. Here's 0 for the middle. I'm not going to be super picky about tick marking on this, just indicating where the numbers are in the 0. Now this one isn't actually equal to any of them. There's no equal line underneath, so I don't have to worry about filling in a bubble. I'll just use these as my markers, the 3 and the 5, and we're looking at values in between. And there we go. So, let's see, interval notation. Start at 3, we don't include it. And we go until 5, but we don't include it. Once again, open parenthesis. And there we go. So I'm going to go ahead and pause here for this video. We'll pick up for the next one at the union of an intersection of sets, objective 3, in the next video.